Let's talk about capacitor charging loss, or the energy lost while charging a capacitor. Let's start with the energy stored in a capacitor, and to find out we use this formula here. This J is for joules, that's the energy, so it's 1/2 the capacitance times the voltage squared. And this Q is our charge in coulombs, and that's equal to the capacitance times the voltage. Now, I've got a capacitor down here, 10 farad at 2.7 volts, and how much energy is stored in this capacitor? Well, we take our 10 times 2.7 squared, divide that by 2, and it comes out to 36 joules stored in this capacitor. Now, if we close the switch here, we'll transfer half the voltage to this capacitor, and we take the joules stored in this one, or it's 10 times 1.35 volts squared, divided by 2. That comes up to 9. This one's the same thing, 9 joules in this one. That's a total of 18 joules. So over here we've got 18 joules, and here we've got 36. We've lost half the energy just by closing the switch and transferring our voltage over to this one. Now, the charge, though, this Q, it's the same. It's 10 times 2.7 is 27. And over here we've got 10 times 1.35 plus 10 times 1.35. That's 27. The charge is conserved, same amount of charge, but we've lost half the energy just charging the capacitor. So we're going to do a little experiment. We're going to take a 10 farad capacitor charged up to 2.7 volts, and then we're going to discharge it through, I showed 10 LEDs here, but we're going to do 20 of them. Now, the energy stored in this capacitor, of course, is the 36 that we calculated before. These leads here, though, when they get down to 1.9 volts, they're gonna shut off. So we're going to leave some energy in this capacitor. So we take 10 times 1.9 squared, divide that by 2. So that's 18 joules that we won't be able to use. So 18 minus the 36, it comes out to about 18 joules that we're going to leave in the capacitor. So how long will these LEDs stay lit for? Well, we have 20 leads, and you know, when we started to 2.7 volts, you might have 20 milliamps, but as this voltage drops off, they'll draw less and less amperage. So I'm just guessing maybe 8 milliamps for an average, and at 2 volts. So we take 20 LEDs times the 8 milliamps. That comes out to 1.6 amps total. And if we take that and times that by our 2 volts, we get 0.32 watts. Okay. Now we take our watts, we divide that into our joules. It comes out to 56 seconds. Now, this if we charge this up and discharge it into these LEDs, they should stay lit for about 56 seconds until the voltage drops to 1.9 volts. Well, we'll see if that math actually works. We'll give that a try. We'll do it right now. All right, here we are. I've got the capacitor charged up to 2.7 volts, and we'll see how long they go if I can push these at the same time. All right, here's our time here. I guessed that at about 56 seconds. We'll see what happens. We're at 2.1 volts now at 20 seconds, 2 volts at 22 seconds, and we'll see what happens here. 1.99, 30 seconds. At 40 seconds, 1.93. And right there we've got 50 seconds. That was off by 6 seconds. So we're going to charge up this capacitor again, discharge it into the other capacitor, put them both in series, and see how long this these LEDs will stay lit for. All right, I've got 2.7 volts, a little over on this capacitor. I'm going to put this one in parallel with it and see how far see what we get. All right, we're at 1.336. It'll take a while to charge that up. That's good. I'll call that good. All right, I've got 2.7 volts on these two capacitors in series, and we'll see how long it lasts. We're going to stop at 1.9 volts. "14 seconds at 2 volts. 1.95. 1.900. 26. Well, about half the time. So I think the math worked out. Anyway, that's what happens when you charge a capacitor. Thank you.